There is a number that most scientists prefer not to mention at press conferences on space exploration. A number so devastatingly large that, when you really understand it, any fantasy of becoming an intergalactic civilization crumbles like a house of cards. That number is 2,100,000 light-years, the distance to Andromeda, our closest neighboring galaxy. To help you understand what this really means, let me put it into perspective. If the Milky Way were the size of a $1 coin in your hand, Andromeda would be another coin located almost 3 meters away. Sounds manageable, right? But now multiply that scale by reality. Every millimeter of that coin represents 1,000 light-years of empty, frozen, lethal space. Voyager 1, our fastest and most distant human object, has been traveling at over 37,000 km/h for 47 years. In all that time, it has barely left our solar system. It hasn't even truly reached deep interstellar space. If we pointed Voyager directly toward Proxima Centauri, the star closest to us, it would take 73,000 years to get there. 73,000 years to travel 4.2 light-years. Now take a deep breath and do the math for Andromeda. With Voyager's technology, it would take us approximately 1.8 billion years to reach the nearest galaxy. 1.8 billion years. By the time we arrived, if anything arrived, the sun would have expanded its atmosphere and evaporated the Earth's oceans. Our planet would be a scorched desert, or perhaps it would not even exist. Humanity would be a forgotten fossil if there were anything left to remember. But you may think that Voyager is old technology, that we can go faster. And technically, you are right. The most optimistic proposals for advanced spacecraft using solar sails or nuclear fusion propulsion could reach between 10 and 20% of the speed of light. Impressive numbers compared to what we have now. At 20% of the speed of light, we could reach Andromeda in approximately 12.5 billion years. 12.5 million years, from the time the first hominids began walking upright in Africa to today. Barely 7 million years have passed. The entire history of humanity, from the first stone tools to smartphones and spaceships, has occurred in a microscopic fraction of that time. And we are talking about the one-way trip only. The reality is that the space between galaxies is not like the space between planets or even between stars. It is an abyss of a scale that our brains, evolved to hunt in the African savannas and gather fruit from trees, simply cannot process. When astronomers say empty space, they don't mean a room without furniture. They mean expanses where you could travel for millions of years without encountering absolutely anything, not a speck of dust, not a stray atom, nothing except perfect darkness and absolute cold at 2.7 degrees above absolute zero. To complicate matters further, that abyss is not still. It is not a calm ocean that we can cross with infinite patience. Intergalactic space is constantly expanding, stretching like an elastic cord that someone is pulling non-stop. With every passing second, Andromeda and we should be farther apart. Except that the mutual gravity between the two galaxies is so strong that we are actually getting closer. But we'll talk about that paradox later. Because what matters now is to understand that we live in a universe where distances are not only enormous, but actively hostile to any attempt to cross them. Think about this. Light, traveling at 300,000 km per second, takes 2.5 trillion years to travel from Andromeda to your eyes. Light has no mass. It doesn't need fuel, it doesn't get tired, it doesn't age. It is literally the fastest thing that can exist in the universe according to the laws of physics. And yet it still takes 2.5 billion years to make that journey. When you look at Andromeda in the night sky, you are seeing how it was when our Australopithecus ancestors were just beginning to make the first tools in Africa. Now imagine trying to send a spacecraft with humans and all the infrastructure necessary to keep them alive. Food, water, air, radiation protection, redundant life support systems, fuel for course corrections, repair equipment, habitable areas, recycling systems. The weight of all that would exponentially multiply the energy needed to reach significant speeds. We're not talking about small differences. We're talking about every additional kilogram requiring astronomical amounts of additional energy. Scientists at NASA and ESA have calculated theoretical missions to the nearest stars, not galaxies, just stars in our immediate neighborhood. And the numbers are daunting. The Daedalus project of the 1970s calculated that a robotic mission to Barnard's star 6 light-years away would require 54,000 tons of helium-3 fusion fuel, 54,000 tons for a 50-year robotic trip to a relatively nearby star. Multiply that by the requirements for a manned trip to a distant galaxy, and the numbers become literally astronomical in the most literal sense of the word. There is another dimension to this problem that is rarely discussed: navigation. At interstellar distances, and even more so at intergalactic distances, navigation errors are magnified exponentially. 1/1000th of a degree error in your initial trajectory could cause you to miss your target by millions of light years. And there is no GPS in intergalactic space. There are no reference satellites. There are no signals you can use for real-time course corrections. You would be navigating by stars that will have changed position by the time you reach your destination, using mathematics that must predict the positions of objects millions of years in the future. Computer simulations of hypothetical intergalactic travel reveal another terrifying problem: gravitational drift. Although the space between galaxies is mostly empty, it is not completely empty. There is dark matter, even though we cannot see it. There are weak but present gravitational fields. Over a journey lasting millions of years, these tiny gravitational influences would accumulate, deflecting your trajectory in ways that are impossible to predict accurately. It would be like trying to make a perfect shot on a pool table the size of a continent with the ball spinning for 1,000,000 years. The odds of success are statistically indistinguishable from zero. And then there is the time factor. Even if we solved all the technical problems, even if we built a ship that could travel at 20% of the speed of light, even if we could keep generations of humans alive for millions of years, what would we find when we arrived? Andromeda will not be where we see it now. It will have moved. The stars within it will have been born and died. Civilizations that might have existed there will have risen and vanished 1,000 times over. We would be chasing a ghost, a mirage of ancient light, trying to reach something that ceased to exist in that form eons ago. The harsh reality is that intergalactic distances are not simply large. They are so immeasurably vast that they render any conceivable technology useless. No matter how advanced we become, no matter what we discover, no matter how long we survive as a species, the chasm between galaxies is, for all practical purposes, infinite. This is our first encounter with the bars of our cosmic cage. The distances between galaxies are not an obstacle we can overcome with enough ingenuity or determination. They are an absolute wall, built by the fundamental geometry of the universe itself. And this is only the first of many walls we will discover. Because even if we could solve the problem of distance, even if we could make light years irrelevant, there are even more fundamental barriers waiting for us. Barriers that make distance seem like the least of our problems. Daly asks, "It's no longer how we will reach other galaxies. The question is, why was the universe designed in such a way that guarantees we will never be able to do so? Intergalactic distances are terrifying, but at least they are a conceptual problem that we can imagine solving with enough time. Perhaps generational ships, perhaps hibernation, perhaps something we have not yet invented. But there is a much more fundamental much more absolute barrier that destroys even the most optimistic fantasies. A barrier that cannot be overcome with ingenuity, patience, or future technology. That barrier is energy. Specifically, the amount of energy required to move any object with mass at speeds that would make intergalactic travel remotely feasible. And when I say amount of energy, I don't mean a lot of energy. I mean amounts so obscenely vast that they make all of humanity's energy reserves look like a spark from a lighter compared to the sun. Let's start with a specific number that will help you understand the magnitude of the problem of accelerating a spacecraft, weighing approximately 1,000 tons, roughly the weight of the International Space Station. To 50% of the speed of light, you would need approximately 1.3 billion terajoules of energy. To put that in perspective, that's more energy than all the electricity generated by all of humanity in all of its history. All the energy from all the power plants, all the nuclear plants, all the solar panels, all the windmills, all the burning of coal, oil, and gas since we discovered fire. All of that combined would not be enough to accelerate a single spacecraft the size of the ISS to half the speed of light. And that's just to accelerate. You need to slow down when you reach your destination, which requires exactly the same amount of energy. So double that number, and remember, we're talking about reaching only 50% of the speed of light, which means the trip to Andromeda would still take 5 million years. But the problem gets exponentially worse as you try to go faster. This is due to one of the most beautiful and ruthless equations in physics, the relativistic kinetic energy equation. At low speeds, energy increases linearly with speed. You double the speed, you quadruple the energy. But as you approach the speed of light, the relationship becomes exponential, then super-exponential, and finally asymptotic. That is, the closer you get to the speed of light, the more energy you need, and that amount grows to infinity. To reach 90% of the speed of light, you would need approximately twice as much energy as to reach 50%. For 99%, you need 10 times more. For 99.9%, you need more than 20 times the energy of 99%. And for 99.99%, the figures become literally astronomical. We are talking about energies equivalent to the total output of the sun for years. Scientists have calculated that to accelerate a 1,000-ton spacecraft to 99% of the speed of light, you would need approximately 4.2 billion tons of fuel. Perfect in a perfect reaction of mass conversion into energy. 4.2 billion tons. For reference, all of humanity consumes approximately 14 billion tons of oil equivalent per year. You would need almost a third of the annual energy consumption of the entire human civilization. But not in the form of oil or coal, in the form of perfect fuel with 100% efficient conversion of mass into energy. And here's the problem. That perfect fuel doesn't exist. The most efficient reaction we know of is the annihilation of matter and antimatter. When 1 kilos of matter encounters 1 kilos of antimatter, they annihilate each other, converting into pure energy according to Einstein's famous equation, E equals EMC squared. It's perfect in theory. Every gram of mass is converted into approximately 90 petajoules of energy. But antimatter doesn't grow on trees. You have to manufacture it. And manufacturing it requires exactly the same amount of energy that it will then release when annihilated. It's like filling a gas tank using the energy you hope to get from that same gas. You end up with a net zero. Worse still, our current methods of antimatter production are appallingly inefficient. For every million units of energy we invest, we get just a few units of usable antimatter. The rest is lost in heat, radiation, and secondary processes. CERN, the world's most powerful particle accelerator, can produce approximately 10 million antiprotons per minute on its best days. That sounds impressive until you do the math. You would need CERN to run continuously for approximately 100 million years to produce a single gram of antimatter. 1 gram. And remember, we need billions of tons. Even if we could magically solve the production problem, storing antimatter is another nightmare altogether. Antimatter cannot touch normal matter, or it instantly annihilates. You need incredibly powerful magnetic fields to keep it suspended in perfect vacuum. Those magnetic fields require continuous energy. And if something goes wrong, if there's a power failure, if a micrometeorite pierces your container, all your antimatter is instantly annihilated in an explosion that would make thermonuclear bombs look small. But let's assume we solve all those problems. Let's say we find a way to efficiently produce and store massive amounts of antimatter. We still face a fundamental problem, the Tsiolkovsky rocket equation. This equation, formulated in the early 20th century, describes a brutal truth about space travel. Most of your spacecraft's weight is fuel, and that extra fuel requires more fuel to accelerate it, which requires even more fuel to accelerate that fuel, and so on in a vicious spiral for intergalactic travel. The ratio of fuel to payload becomes absurd. Some calculations suggest ratios of 1 million to 1. For every kilogram of payload, instruments, crew, food, water, you would need 1 million kilograms of fuel. And that 1 million kilograms needs to be accelerated as well, which requires more energy, which requires more fuel. It's a paradox that feeds back on itself to the point of mathematical collapse. Engineers have proposed creative solutions, Buzar stator engines, for example, which would collect hydrogen from interstellar space and use it as fuel for continuous nuclear fusion. In theory, you would never run out of fuel because you would be collecting it as you travel. Problem solved, right? Not exactly. The most recent calculations show that the density of hydrogen in interstellar space is so low that you would need a collector the size of a country to collect useful amounts. And in intergalactic space, where the density is 1,000 times lower, you would need a collector the size of a solar system. The structural forces needed to hold something like that together at relativistic speeds would instantly tear it apart. Others have suggested solar sails propelled by giant lasers from Earth. The idea is that the spacecraft carries no fuel. The energy comes from lasers pushing it from home, but again, the numbers are devastating. To accelerate a reasonably sized spacecraft to relativistic speeds using lasers, you would need a laser facility that consumed the total energy output of the sun, literally. And you would need to keep that laser perfectly focused on a spacecraft moving away at relativistic speeds for decades or centuries. A targeting error of 1,000th of a second, and you lose the spacecraft forever. There is also the proposal for nuclear bombs. The Orion project of the 1960s suggested dropping nuclear bombs behind a spacecraft and riding the shockwave. It would work in theory. In fact, it is one of the few propulsion proposals that we could actually build with current technology. The problem is that you would need millions of nuclear bombs. Millions. For a trip to the nearest star. For an intergalactic journey, you would need more nuclear bombs than there are atoms on Earth. Obviously impossible. Every proposed solution eventually hits the same wall. The energy required for intergalactic travel exceeds the energy available in the system we want to use. It's like trying to empty the ocean using ocean water. No matter how efficient your bomb is, it will never work because the task requires more resources than the system can provide. And this brings us to the most devastating revelation of all. Even if we could build a perfect antimatter engine, even if we could solve all the engineering problems, even if we could collect unlimited amounts of energy from the sun or nuclear fusion, we would still run into an absolute barrier. The speed of light is not just a speed limit, it is an energy limit. As you approach the speed of light, the energy required to accelerate even 1 more gram approaches infinity. Literally infinity. No matter how much energy you have, it is never enough to reach the speed of light, because the universe has placed a wall of infinite energy right at that limit. Physics is not being cruel. Physics is being absolute. The laws that allow energy to exist, that allow atoms to exist, that allow you to exist reading these words, are exactly the same laws that guarantee that you will never be able to accelerate fast enough to make intergalactic travel viable. It's not a question of technology. It's not a question of time or patience or ingenuity. It's a question of fundamental laws of the universe that cannot be broken, bent, or circumvented. The energy barrier is not an obstacle we can eventually overcome. It is an absolute wall inscribed in the very fabric of reality. And this wall has an even more devastating consequence that we haven't discussed yet. A consequence that makes the problems of distance and energy seem trivial in comparison. Because even if we solved both, even if we found a magical way to travel fast without impossible energy, there is a third barrier waiting for us. A barrier that guarantees that any intergalactic traveler would be doomed to a fate worse than death, absolute and eternal isolation from the rest of humanity. Imagine we finally succeed. Imagine we solve the problems of distance and energy with some miraculous future technology. We build a ship that can travel at 90% the speed of light and send it to Andromeda with a crew of brave explorers. It is the greatest moment in human history. Cameras broadcast as the ship moves away from Earth, crosses the Moon's orbit, passes Mars, Jupiter leaves the solar system, and enters the interstellar abyss. And then something happens that no one fully anticipated in the simulations. Something that physicists knew would happen, but whose existential implications had never really been discussed in public. Messages from the ship begin to arrive more and more spaced out. Not because the crew is sending fewer messages, but because each signal takes longer to arrive. After a year, there is a 1-year delay. After 10 years, a 10-year delay. After 100 years, your great-great-grandchildren are receiving messages from people who died decades ago. But this is only the beginning of the problem. The real horror begins when you consider what happens to radio signals at relativistic speeds. When something moves very fast away from you, the electromagnetic waves it emits are stretched. This is the famous Doppler effect, the same one that makes an ambulance siren sound lower when it moves away. But at speeds close to the speed of light, this effect not only changes the pitch, it completely destroys the signal. A radio signal sent from a spacecraft traveling at 90% of the speed of light undergoes extreme redshift. The frequencies are stretched so much that a signal sent in the FM radio band would reach Earth as extremely low-frequency radio waves, almost undetectable. And this worsens exponentially with speed. At 99% of the speed of light, signals are stretched so much that they become virtually impossible to detect, even with the most sensitive radio telescopes. But the Doppler effect is only the first layer of this communication hell. Something much worse awaits: time dilation. Einstein proved that time is not absolute. Time flows at different speeds depending on how fast you are moving. At normal speeds, this difference is microscopically irrelevant. But at relativistic speeds, the difference becomes dramatic, devastating, existential. For a spacecraft traveling at 90% of the speed of light, for every year that passes for the crew, approximately 2.3 years pass on Earth. Sounds manageable, right? A discrepancy you could compensate for in your calculations. But at 99% of the speed of light, the ratio is 1 to 7 for every year of the crew, 7 years on Earth at 99.9%. It is 1 to 22 at 99.99%, and 1 to 70. Now think about what this means for communication. Imagine you are part of the crew and you send a message to Earth saying, "All is well. We have completed the first year of the 1900 journey." That message travels at the speed of light back to Earth. But while that message is traveling, Earth continues to age much faster than you. By the time your first year completed message reaches Earth, decades have passed. Your children are elderly. Your grandchildren have grandchildren. The world you left no longer exists. And when Earth responds to your message, its response takes decades to reach you. But to you, feeling it in subjective time, it seems as if Earth simply stopped responding. The messages arrive more and more spaced out, more and more out of sync with your reality. The responses you receive are to questions you asked months ago according to your clock, but which were sent decades ago according to Earth's clock. A study published in 2024 by physicists at Oxford University modeled exactly this scenario and came to a devastating conclusion. At speeds necessary to make intergalactic travel viable, coherent two-way communication becomes physically impossible. Not difficult, not complicated, impossible. The temporal desynchronization is so severe that any attempt at conversation collapses into chaos, with messages arriving in the wrong order, with lost contexts, with references to events that have not yet happened or that happened so long ago that they are no longer relevant. Imagine trying to have a conversation where every word you say takes a year to reach the other person, and their response takes another year to get back to you. But also, time is flowing at different speeds for both of you. It would be like trying to play chess by mail if the letters arrived randomly out of order and the other person aged 10 years for every move you made. But there is an even deeper layer of horror to this problem. It's not just that communication is difficult or delayed. It's that eventually it becomes literally impossible to maintain a coherent signal. Electromagnetic signals lose energy as they travel. They scatter, weaken, and become contaminated with cosmic noise. At interstellar distances, you need massive antennas and enormous transmission powers just to send simple messages. At intergalactic distances, the amount of energy required to send a detectable signal becomes prohibitive. Scientists calculate that to send a simple radio message from Andromeda to Earth that could be detected by our most powerful radio telescopes, you would need an antenna the size of a planet, transmitting with a power equivalent to the total output of several stars. And that's just to send something equivalent to a few words. To send video, audio, complex scientific data, you would need such vast amounts of energy that you would basically need a Type 2 civilization on the Kardashev scale, one that can harness all the energy of its star. And this assumes that both ends of the communication are stationary. But remember, the ship is traveling at relativistic speeds. The Doppler effect is distorting all frequencies. Time dilation is desynchronizing all clocks, and the distance is constantly increasing. Every second that passes, the ship is millions of kilometers farther away. Every day, tens of billions of kilometers. Every year, distances that defy comprehension. There is also another phenomenon that is rarely mentioned: relativistic light aberration. At speeds close to the speed of light, your perception of the universe changes radically. The stars in front of you seem to concentrate into a bright spot, while the stars behind you disappear. The entire sky is distorted, and the signals you receive from Earth do not come from where you expect. They arrive angularly displaced due to your extreme speed. You need to constantly calculate where to point your antennas, not where you see Earth, but where Earth will be when your signal arrives, compensating for both your movement and time dilation. The complexity of maintaining communications under these conditions is not only technical, it is existential. You are trying to maintain contact with a world that is aging at different rates, that is separated by distances that make signals take years, decades, or centuries to travel. Where every message you send is a time capsule of a version of yourself that technically no longer exists by the time the message arrives. Psychologists who have studied extreme isolation in Antarctica, in nuclear submarines, in space simulation missions, all agree on one thing. Humans need regular social connection to stay sane, not occasional, regular, daily, ideally. When that connection is delayed too long, when responses take weeks instead of seconds, human psychology begins to break down. People develop depression, anxiety, psychosis. Now imagine that responses don't take weeks. They take years, decades. That every message you send is essentially a letter thrown into the void, with no real hope of a meaningful response. That each passing day takes you further away from the only species with which you can genuinely communicate. That you are condemned to spend the rest of your life and the lives of your children and the lives of your children's children in such complete isolation that no human being in history has ever experienced. This is not exploration. It is exile. It is voluntary banishment to a loneliness so profound that it becomes a form of death in life. You would still be alive. You would still think, feel, exist. But you would be completely, irrevocably separated from everything that makes human life meaningful. No real-time conversations, no love shared in the moment, no ability to comfort someone who is suffering or celebrate with someone who is succeeding. And here is the cruelest paradox of all. The very speed that makes travel possible is what makes connection impossible. To travel fast enough to make intergalactic travel feasible within a human lifetime, you need to go so fast that communication breaks down completely. You can't have both. It's physically impossible. You can reach another galaxy or you can maintain contact with home, but you can't do both. The universe forces you to choose, and both options are variations on tragedy. Intergalactic travelers would not be explorers. They would be ghosts, entities trapped between worlds, unable to return to the one they left behind or truly belong to the one they are trying to reach, wandering the abyss for generations, sending messages that no one will answer in time, receiving echoes from a world that died long ago, condemned to a form of existence that no conscious being should ever experience. And this cosmic loneliness is not the only problem travelers face. Because as they float in that absolute silence, as Earth ages at different rates and communications fade into cosmic noise, the universe itself is actively working against them in a way that makes all previous problems seem trivial. An invisible, unstoppable force that ensures that every second they spend traveling, their destination moves further away, faster than they are getting closer. There is a force in the universe that few truly understand. A force so strange and counterintuitive that when it was first discovered, even the world's best physicists refused to believe it. A force that neither pushes nor pulls, that has no identifiable source, that cannot be blocked or avoided. A force that is, at this very moment, pushing every galaxy away from every other galaxy at ever-increasing speeds. That force is the expansion of space itself. In 1929, astronomer Edwin Hell made a discovery that forever changed our understanding of the cosmos. He observed that virtually all distant galaxies were moving away from us. And strangest of all, the farther away a galaxy was, the faster it was moving away. It wasn't that the galaxies were moving through space. It was that the space itself between us and them was expanding, stretching like a cosmic rubber band that someone is pulling non-stop. The relationship he discovered is now known as Hubble's law, named after Hubble and Belgian priest Georges Lemaitre, who first proposed the idea mathematically. The law is deceptively simple. For every 326 million light-years away, galaxies are moving away from us at approximately 70 kilometers per second faster. 70 kilometers per second per megaparsec in astronomical terminology. It sounds like a small number until you start doing the math. Andromeda, 2.5 trillion light-years away, should be moving away from us at approximately 54 kilometers per second due to expansion. In fact, it is approaching us at approximately 110 kilometers per second because the mutual gravity between the two galaxies is strong enough to overcome the expansion. We are the exception. Andromeda and the Milky Way are destined to collide in about 4 billion years. But beyond our local group of galaxies, beyond the few dozen galaxies that are gravitationally bound to us, expansion completely dominates. A galaxy 300 million light-years away is receding at approximately 6 kilometers per second. A galaxy 3 billion light-years away is receding at 65,000 kilometers per second. And this is where everything completely falls apart at approximately 14 billion light-years away. Galaxies are receding from us at the speed of light. Read that again because it's important. At 14 billion light-years away, approximately the size of the observable universe, galaxies are moving away at 300,000 kilometers per second. And beyond that point, they are moving away faster than the speed of light. This does not violate special relativity because the galaxies are not moving through space faster than light. It is the space between us and them that is expanding faster than light can cross it. This is the ultimate cosmic trap. Imagine you are on a giant cosmic treadmill that is constantly accelerating. No matter how fast you run, the treadmill moves faster. Eventually, you reach a point where even running at the maximum possible speed, the speed of light, you are still moving backward instead of forward. That is exactly what potential intergalactic travelers face. Now, Andromeda is special because it is close enough that gravity overcomes expansion. But let's say we aim for another galaxy, one that's farther away, the Triangulum galaxy, for example, at about 3 million light-years, or the M87 galaxy at about 55 million light-years. For these galaxies, expansion is actively working against us. The calculations are brutally simple and devastating. If we built a ship that could travel at 99.99% of the speed of light and aimed it at a distant galaxy during the journey, the space between us and that galaxy would continue to expand. Every year we travel, the target distance increases not only by the space we haven't yet crossed, but by the new space being created as we travel. It's like trying to swim to shore while the current pulls you out to sea. Except this current doesn't just pull you back, it constantly accelerates. With every stroke you take, the current gets a little stronger. And there's no way to swim faster, because you're already swimming at the maximum speed that physics allows. A 2022 study by the California Institute of Technology modeled exactly this scenario. They calculated that for a galaxy located more than 4.6 billion light-years away, known as the Hubble horizon, it is physically impossible to reach it, no matter what technology you use. Even traveling at the speed of light, for the entire current age of the universe, you would never reach it because the space in between is expanding faster than you can cross it. This means that approximately 94% of the galaxies in the observable universe are already beyond our reach. Not because they are too far away in the traditional sense, but because space is expanding so fast that we will never be able to send even light to reach them. They are observable in the sense that we can see the light they emitted billions of years ago. But they are unreachable in the sense that we will never be able to visit them. And it gets worse. The expansion of the universe is not constant. It is accelerating. In 1998, two independent teams of astronomers discovered that the universe is not only expanding, but expanding faster with each passing year. They won the Nobel Prize in Physics in 2011 for this discovery. This acceleration is attributed to something called dark energy, a mysterious form of energy that permeates all of space and pushes the universe to expand faster and faster. The practical consequence of this is terrifying. The horizon of reach is shrinking. Galaxies that we could theoretically reach today, if we had the technology, will be beyond our reach in 1 million years. Galaxies that will be beyond our reach in 1 billion years will be beyond our observable horizon in 10 billion years. The accessible universe is shrinking as we speak, slowly disappearing behind a cosmic event horizon that we will never be able to cross. Think about the existential implications of this. There are civilizations in distant galaxies at this very moment. Civilizations that may be looking at our night sky, wondering if there is anyone else out there. And we are here wondering the same thing about them. But because of cosmic expansion, we will never meet, never exchange signals, never share knowledge. We are permanently isolated, not by choice or lack of technology, but by the fundamental structure of space-time. And this applies even to galaxies within our current theoretical reach. Andromeda, which we could reach because gravity outweighs expansion, is the rare exception for virtually every other galaxy, even those within hundreds of millions of light years. Expansion means that the journey would take much longer than the current distance suggests, because you would be chasing a target that is constantly moving away. Imagine aiming for a galaxy 500 million light-years away, with a ship traveling at 99.99% of the speed of light. Calculating only the travel time without considering expansion, you would need approximately 500 million years. But during those 500 million years, space has expanded. The target galaxy is now approximately 600 million light-years away. You need to travel another 100 million years. But during those 100 million years, it expands further. It's a race you can never win because the goal moves away faster than you can run. Mathematicians call this an asymptotic limit. You get closer to your goal, but you never fully reach it. It's like trying to reach the horizon. You walk toward it, and it always seems to be the same distance away, always unreachable, always beyond your next step. And then there is the even darker reality of accelerated expansion. Cosmologists predict that in about 100 billion years, due to the continued acceleration of expansion, all galaxies outside our local group will have disappeared beyond the cosmological horizon. Their light will never reach us. They will vanish from the night sky as if they had never existed. Future civilizations in our galaxy will look up at the sky and see only darkness. They will have no way of knowing that there was once a larger universe filled with billions of other galaxies. This is perhaps the loneliest possible form of universe, one where intelligent life inevitably arises, looks up at the cosmos, and is permanently isolated from any other intelligent life by forces it cannot control, overcome, or even resist. The universe is designed by pure chance of its fundamental laws to keep civilizations isolated on increasingly smaller cosmic islands. But here is the ultimate paradox. Even if we could somehow overcome expansion, even if we found a way to travel faster than space expands, we still run into the barriers we already discussed. Energy remains impossible, distances remain insurmountable, communication remains unfeasible. The expansion of the universe is not the only problem. It is simply another nail in the coffin of intergalactic dreams, another fundamental law that says no in the most absolute way possible. And this law has a silent accomplice, another aspect of physics that guarantees our imprisonment, an accomplice that has nothing to do with distances or energy or cosmic expansion, an accomplice that is within the very equations that describe how time, space, and speed work. Einstein's equations, which when fully understood reveal that even in a universe without expansion, even with infinite energy, we would still be prisoners of our own galaxy for reasons that are perhaps the most fundamental of all. In 1905, a 26-year-old employee of the Swiss Patent Office published an article that would forever change our understanding of the universe. Albert Einstein, a name we all know now, proposed something so radical, so counterintuitive, that even today, more than 100 years later, our minds struggle to fully accept it. He proposed that time is not absolute, that space is not fixed, that both are malleable, flexible, observer-dependent, and most importantly for our discussion, that nothing with mass can reach the speed of light. This last statement is not a suggestion. It is not a technological limitation that we can overcome with enough ingenuity. It is a fundamental law of the universe, as inviolable as the conservation of energy or the fact that 2 + 2 = 4. And this law has devastating consequences for any civilization that dreams of intergalactic travel. The central problem lies in an equation called the Lorentz factor, represented by the Greek letter gamma. This equation describes how time, mass, and length change as you approach the speed of light. At normal speeds, the Lorentz factor is practically 1, meaning there are no noticeable effects. Your car traveling at 100 km experiences relativistic effects so microscopic that they are completely irrelevant. But as you approach the speed of light, the Lorentz factor begins to grow. At 50% of the speed of light, it is approximately 1.15. This means that your clock runs approximately 15% slower than the clock of someone at rest. It doesn't sound that dramatic, does it? But watch what happens as you accelerate further. At 80% of the speed of light, the factor is 1.67. At 90%, it's 2.30. At 95%, it's 3.2. At 99%, it's 7.1. You can already see the trend. The numbers start to grow faster and faster. At 99.9%, music of the speed of light, the Lorentz factor is 22.4. At 99.99%, it's 70.7. And here's the deadly problem. For intergalactic travel to be feasible within a human lifetime, you need enormous Lorentz factors. Andromeda is 2.5 trillion light-years away. Even at 50% of the speed of light, it takes 5 million years according to Earth time. Useless, even at 99% of the speed of light. That's approximately 2.5 trillion years of Earth time, although for you it would be approximately 350,000 years, thanks to time dilation. Still completely unfeasible. To reduce the travel time to something remotely practical, say 100 years of subjective time for the crew, you would need a Lorentz factor of approximately 25,000. This corresponds to a speed of 99.99998%, 999,999.8% of the speed of light. And this is where relativistic physics twists the knife. The energy required to reach that speed is absolutely prohibitive. Recall the relativistic equation for kinetic energy. At low speeds, energy is simply a matter of mass multiplied by velocity squared. Simple, linear, manageable. But at relativistic speeds, the equation transforms. Relativistic kinetic energy is mass multiplied by C2AD multiplied by the Lorentz factor. 1. And when the Lorentz factor is 25,000, you are multiplying the mass of your ship by 25,000 times the speed of light squared. The numbers become obscene. For a 1,000-ton ship, the energy required to reach a Lorentz factor of 25,000 is approximately 2.2 10 to the power of 24 joules. To put that in perspective, that's roughly the energy the sun emits in 2 full weeks. You would need to capture all the energy from the sun for 2 weeks and focus it perfectly on accelerating your ship. And that's just to accelerate. You need the same amount to slow down, and this assumes perfect efficiency, which is physically impossible. In reality, With the efficiencies we can achieve, you would probably need 100 times more energy. We are talking about the total output of the sun for almost 3 years for a single ship, a single trip. But even if we could magically solve the energy problem, relativity has other unpleasant surprises waiting for us. One of the most disturbing is the twin paradox, amplified to an intergalactic scale. Do you know the basic version? One twin travels into space at relativistic speeds while the other stays on Earth. When the traveler returns, they have aged less than the twin who stayed at home. It's a real effect verified experimentally 1,000 times. Now amplify this to an intergalactic journey. Imagine you leave for Andromeda with a Lorentz factor of 25,000. For you, the trip takes 100 years. You live a whole lifetime exploring during the trip. Maybe you have children, even grandchildren. Finally, you decide to return home. Another century of subjective time, 200 years total for you. But when you return to Earth, approximately 5 million years have passed. 5 million. The civilization you knew no longer exists. The language you speak is unintelligible. Your friends, family, your entire species as you knew it. Everything has disappeared eons ago. The continents have shifted, species have evolved. The Earth you left behind is literally an alien world. Now there is no way back home. Technically, you return to the same planet, but that planet has changed so much that you might as well be on another world. You are a timeless ghost, a living anachronism, someone completely disconnected from your own time. This is not speculative science fiction. It is a direct mathematical consequence of Einstein's equations. Inevitable, inescapable, absolute. There is also the problem of relativistic mass. As you accelerate, your effective mass increases by the Lorentz factor. This does not mean that you gain additional atoms, but rather that your inertia increases. It becomes more and more difficult to accelerate further. At 99.99% of the speed of light, your effective mass is 70 times greater than your rest mass. This means that any force you try to apply to accelerate further has to overcome 70 times more inertia. And this creates a vicious feedback loop. You need more energy to accelerate further, but as you accelerate, your effective mass increases, requiring even more energy to accelerate, which increases your effective mass even further. It's an exponential curve that shoots off to infinity. As you approach the speed of light, your effective mass approaches infinity, and the energy required to give you even a little extra acceleration then also approaches infinity. This is not rhetorical hyperbole. It is mathematically literal. At the limit where your speed approaches c, the speed of light, your effective mass diverges toward infinity. It would require infinite energy to accelerate an object with mass to exactly the speed of light. Infinity, not a very large number, literally infinity. The universe has placed a wall of infinite energy right at that limit, ensuring that you can never cross it. And there's more. At extremely relativistic speeds, the universe in front of you begins to behave in strange ways. The normally harmless photons of the cosmic microwave background, with temperatures of just 2.7 degrees Kelvin, undergo such extreme blue shift that they become deadly gamma radiation. At a Lorentz factor of 25,000, these photons would reach your ship with energies equivalent to high-energy gamma rays, constantly bombarding you with lethal radiation. Engineers have calculated that you would need shields several meters thick, made of dense materials, just to protect yourself from this radiation. But those shields have mass, and that additional mass requires more energy to accelerate, and more mass for fuel, and more shields to protect that fuel. It's another vicious spiral with no elegant solution. Even interstellar dust, normally invisible and irrelevant, becomes a deadly hazard at extreme relativistic speeds. A dust particle the size of a grain of sand hitting your ship at 99% of the speed of light would release energy equivalent to several atomic bombs. Every speck of dust is potentially a catastrophic explosion. You would need to constantly detect and avoid them, or have shields so massive and resistant that the additional weight would make the journey impossible. Then there is the problem of relativistic navigation. At speeds close to light, the stars in front of you appear to concentrate into a bright circle due to the aberration of light. The stars behind you disappear. Your perception of the entire cosmos becomes distorted. Calculating trajectory becomes incredibly complex, because you have to compensate not only for the movement of your target during the journey, but also for the relativistic effects on your perception of space-time itself. And all this assumes that you can accelerate and decelerate smoothly. But humans can only tolerate a certain amount of acceleration before dying, approximately 3 to 4 times Earth's gravity sustained over long periods to accelerate to 99%. 9% of the speed of light, with an acceleration of 3 gravities, would take approximately 1 year. That seems manageable, but that year of acceleration requires massive amounts of fuel being burned constantly. And then you need another year of deceleration upon arrival, and the same for the return trip. That's a total of 4 years of acceleration and deceleration for a single round trip. During all that time, you're burning fuel at phenomenal rates. Calculations show that for a complete trip to Andromeda and back, even with perfect antimatter propulsion, you would need to carry approximately 99.99% of your ship's mass as fuel. Only 0.01% can be payload, crew, instruments, everything else. That means that to have a 1,000-ton habitable module, you would need a ship with an initial mass of nearly 10 million tons. 10 million tons. For reference, the largest ship ever built, the supertanker Seawise Giant, weighed approximately 650,000 tons. You would need to build something 15 times more massive than the largest ship in human history. Except this would have to operate in the vacuum of space, withstand extreme radiation, and burn antimatter in a perfectly controlled manner for years. Relativity isn't cruel. Relativity is utterly indifferent. The very equations that beautifully describe how the universe works, that predict with perfect accuracy the behavior of everything from subatomic particles to black holes, are the same equations that forever close the doors to intergalactic travel. Not because Einstein said no, but because the mathematical structure of space-time itself says no. And these relativistic barriers assume that we can build the ships, generate the energy, and solve all the engineering problems. But there is one final obstacle that we have not yet discussed. An obstacle that has nothing to do with physics or mathematics or engineering. An obstacle that lies within ourselves. Our fragile bodies evolved to thrive on the surface of a specific planet, surrounded by a protective magnetic field, bathed in radiation from a specific star. Bodies that, when you take them out of that perfect environment and throw them into the intergalactic abyss, simply fall apart. We have talked about impossible distances, prohibitive energies, broken communications, and a universe that expands to push us away from our destinations. We have discussed the barriers of relativity that make time itself an enemy. But there is one final barrier that is perhaps the most intimate, the most personal, the most devastating of all. A barrier that is not in the stars, nor in equations, nor in fuel limits, but in our own bodies. Humans evolved over millions of years in a very specific environment. The surface of the Earth bathed in radiation from a G-type star, protected by a planetary magnetic field that deflects lethal charged particles, surrounded by an atmosphere that filters out the most harmful ultraviolet rays, with a precise gravity of 9.8 - 2. Every cell in your body Every biological system, every metabolic process is optimized for these exact conditions. And when you leave that protective environment, when you venture into deep space, and especially into the intergalactic abyss, your body begins to fail in ways that are both inevitable and terrifying. Let's start with radiation. On Earth, you are protected by two invisible but absolutely crucial shields. The Earth's magnetic field deflects most of the solar wind, those charged particles that the sun constantly throws into space. The atmosphere absorbs cosmic radiation, those high-energy protons and atomic nuclei that constantly rain down from deep space. Together, these shields reduce your exposure to radiation to levels that your body can handle, that your DNA can repair. In interplanetary space, say on a trip to Mars, you lose atmospheric protection, but you still have some protection from the solar magnetic field. Radiation exposure increases dramatically. Astronauts on the International Space Station receive approximately 50 to 200 times more radiation than on the Earth's surface. This is enough to significantly increase their risk of cancer, but manageable for missions lasting a few months. In interstellar space, you lose even the protection of the solar magnetic field. Cosmic radiation hits you unfiltered, but at least you are still within the Milky Way, where the galactic magnetic field provides some minimal protection. NASA studies estimate that a decades-long interstellar journey would expose astronauts to doses of radiation doses that would almost certainly cause cancer. But in intergalactic space, all of this disappears. There is no galactic magnetic field to protect you. There is no solar heliosphere. There is nothing except absolute vacuum and unfiltered radiation coming from all directions. Cosmic rays of energy so high that they can penetrate meters of shielding. Particles that can fragment atomic nuclei in your cells, creating secondary cascades of even more damaging radiation. The calculations are brutal, even with several meters of shielding made of water or polyethylene, materials that are relatively good at blocking radiation. An intergalactic traveler would receive cumulative doses that would destroy their bone marrow, collapse their immune system, and guarantee multiple aggressive cancers. And that extra shielding has mass. Mass that needs to be accelerated. Mass that makes the energy problem even more impossible. Some have proposed using artificial magnetic fields to deflect charged particles, essentially recreating the Earth's magnetic field around the ship. But the fields needed would have to be enormous, on the order of kilometers in diameter, and would require massive amounts of energy to maintain continuously for millions of years, and they would only protect against charged particles. Gamma rays, neutrons, and other forms of uncharged radiation would pass right through any magnetic field as if it didn't exist. Then there is the problem of time. Even if we could protect you perfectly from radiation, even if we could create an impenetrable shield, intergalactic travel takes an incomprehensibly long time. We have discussed the millions of years required even at relativistic speeds. And humans don't live for millions of years. We live for decades, 80 years if we're lucky. The obvious solution is hibernation or suspended animation, freezing the crew, putting them into some kind of metabolic stasis, waking them up upon arrival. Science fiction makes it seem simple. The reality is devastatingly more complicated. We have managed to preserve cells, small tissues, even some organs through cryopreservation. But a whole human, an integrated system of interdependent organs with a brain containing 86 billion neurons each, with thousands of synaptic connections, is incomparably more complex. When you freeze living tissue, the water inside the cells forms ice crystals that pierce the cell membranes like microscopic blades. The cells burst. The tissues disintegrate. Scientists have developed chemical cryoprotectants that prevent the formation of ice crystals. They work reasonably well for small samples. But for a complete human body, you would need to perfuse these chemicals through every tissue, replacing all the water in every cell. And these chemicals are toxic in high concentrations. The dose needed to protect you completely would probably kill you before you could be frozen. Even if we solve the freezing problem, the thawing problem is equally difficult. You need to heat the body perfectly evenly. If some parts heat up faster than others, the temperature gradients cause massive structural stress. Tissues would crack, organs would fail, and the brain, the most delicate structure of all, would be particularly vulnerable. Your memories, your personality, everything that makes you you, is stored in incredibly fragile patterns of synaptic connections. A single error in the thawing process could irreversibly destroy them. And this assumes that the hibernation process is performed only once. You freeze, you travel, thaw. But on a journey lasting millions of years, problems requiring intervention will inevitably arise. System failures, meteor damage, the need for course corrections. Someone needs to be awake to handle emergencies, which means multiple cycles of freezing and thawing. Each cycle accumulates more damage. After dozens or hundreds of cycles over millennia, the cumulative damage would likely be lethal. Alternatively, you could have generational ships so large that an entire population lives, reproduces, and dies during the journey. The great-great-grandchildren of the great-great-grandchildren of the original crew eventually reach the destination. But this introduces a whole different set of biological problems. To maintain a genetically viable population for millions of years, you would probably need at least several thousand individuals. Any smaller population would suffer from inbreeding depression, accumulation of deleterious mutations, eventual genetic collapse, and those thousands of people need food, water, air, and living space. You need complete, closed ecosystems that can reliably recycle all resources for eons without fail. A single collapse in water recycling or food production, and the entire population dies. Experiments in closed biospheric systems here on Earth have been consistently discouraging. Biosphere 2. The most ambitious experiment of this type collapsed after only 2 years. Oxygen fell to dangerous levels. Carbon dioxide rose. Species began to die out, and that was with only 8 people in a relatively large, well-designed environment, with the Earth just outside if something went wrong. Now imagine maintaining a closed ecosystem for 2 million years, over 100,000 human generations. The odds of nothing failing catastrophically during that time are statistically indistinguishable from zero. A pest killing a critical crop, a mutation in recycling bacteria rendering them ineffective, a cascading failure where one collapsing system triggers the collapse of others. Any of these errors would be the end of the entire mission. But even assuming perfect ecosystems, there is the psychological problem. Humans did not evolve to live in confined spaces for generations. We evolved as nomads in open spaces, with distant horizons and changing skies. Prolonged confinement causes depression, anxiety, psychosis. Studies in nuclear submarines, Arctic stations, high-security prisons all show the same pattern. Prolonged confinement degrades mental health, even in the most stable individuals. And we are talking about confinement for years or decades, if not for the entire lives of thousands of generations. Children born on a ship live their entire lives without ever seeing a real horizon, without feeling rain, without walking on solid ground. And then they die knowing that their children will experience exactly the same thing. The likelihood of social collapse, rebellion, and violence is extremely high. Some psychological studies suggest that after several generations, The population would even lose the motivation to continue the mission. Why should the great-great-grandchildren of the original crew care about reaching a destination they will never see, following the dream of ancestors who died centuries ago? They would likely eventually reject the mission, change course, or simply let the systems collapse, because the idea of a destination has become abstract and meaningless. There is also the problem of evolution. Over millions of years in an artificial environment, humans would inevitably evolve. Natural selection would favor traits adapted to the environment of the ship, not the environment of the destination. By the time they arrived, if they ever did, they could be a completely different species. Their bodies adapted to artificial gravity, their eyes adapted to artificial light, their immune systems never exposed to natural pathogens. They would be unable to survive on a real planet, even if they found one. And then there is the most fundamental problem of all: purpose. Intergalactic travel would take so long that the civilization that initiates it would bear no resemblance to the civilization that benefits from it. Ships launched today would arrive in an era where humanity, as we know it, probably no longer exist, replaced by post-humans, artificial intelligences, or perhaps nothing at all, if we become extinct in the meantime. Does it make sense to invest astronomical resources in a mission that will benefit entities so distant from us in time and evolution that they would effectively be alien? Does it make sense to condemn generations of humans to live and die in transit to achieve a goal that they may not even remember why it was important? Human biology is not a technical obstacle that we can engineer around. It is a fundamental limitation that reflects the fact that we are products of a specific planet, evolved over eons to thrive in very particular conditions. Removing ourselves from those conditions for cosmological periods of time is not exploration. It is a slow form of extinction. Every system in your body is screaming that we were not designed for this, that our place is here, on this planet, under this star, protected by these magnetic fields, that dreams of becoming intergalactic nomads are fundamentally incompatible with the reality of what we are as biological organisms. And all these biological barriers operate alongside the physical barriers we already discussed. They are not separate problems that you can solve one by one. They are intertwined aspects of a single, devastating truth. The universe, in its fundamental structure, ensures that biological species remain confined to their galaxies of origin. Distances are impossible. Energies are prohibitive. Communication breaks down. Space expands. Relativity imposes absolute limits, and our own fragile bodies collapse under the conditions of deep space. But perhaps there is a glimmer of hope in all this despair. Perhaps if we could at least fully comprehend how vast the universe is, how insignificant we are on its scale, we might find some comfort. So let's explore exactly that, the brutal reality of cosmic distances and what they really mean when you map them out with ruthless precision. There is a reason astronomers use terms like light years or parsecs of kilometers. It's not scientific pretension or unnecessary jargon. It's because the numbers in kilometers become so absurdly large that they lose all meaning. When you say that Andromeda is 24 quintillion kilometers away, your brain simply cannot process it. That is a number without context, without scale, without emotional meaning. But when you really understand what that distance means, when you map it against what we can actually do, the despair becomes palpable. Let's start with something we can comprehend. The Moon is approximately 384,400 kilometers from Earth. Humans have been there. 12 people have walked on its surface. The trip took approximately 3 days with 1960s technology. It's far away, but reachable. It is the only frontier in space that we have actually crossed with our own bodies. Mars, our next target, is on average about 225 million kilometers away, approximately 586 times farther than the moon. With current technology, a manned trip would take between 6 and 9 months. It is challenging, but feasible. Engineers are working hard on manned missions to Mars. We could do it in the next decade or two if we really commit to it. Now let's take the next leap. Proxima Centauri, the closest star to our Sun, is 4.24 light-years away. That's about 40 trillion kilometers. To put that in perspective, if the distance to the Moon is 1 centimeter on a model scale, Proxima Centauri would be more than 3 kilometers away. With the technology of the Year 1 buoy, our fastest spacecraft, it would take us approximately 73,000 years to get there. 73,000 years. The entire human civilization from the first cities in Mesopotamia to today is barely a third of that time. The most optimistic proposals for advanced propulsion, such as the Breakthrough Starshot project, which plans to use solar sails powered by giant lasers, suggest that we could send microscopic probes to Proxima Centauri in approximately 20 years. Traveling at 20% of the speed of light, microscopic probes, not humans, not even car-sized robots, but chips the size of your fingernail with tiny cameras. And that's the best we can conceive of with known physics and an investment of billions of dollars. For a manned mission to Proxima Centauri using realistic propulsion, we're talking about journeys of several centuries, multiple generations living and dying in transit. And that's just to get to the nearest star. Just to cross approximately 0.0004% of the diameter of the Milky Way. The Milky Way is approximately 100,000 light-years in diameter. We are located approximately 26,000 light-years from the galactic center in one of the spiral arms. If we wanted to travel to the other side of our own galaxy, say 80,000 light-years away, with breakthrough starshot technology, it would take 400,000 years. 400,000 years. Neanderthals walked across Europe 400,000 years ago. Homo sapiens as a species has only been around for 300,000 years. And remember, that's within our galaxy. That's our cosmic backyard. Now let's jump into the intergalactic abyss. Andromeda, at 2.5 trillion light-years away, is approximately 25 times more distant than the entire diameter of the Milky Way. And our entire galaxy is the size of a $1 coin. Andromeda is more than 2 million light-years away, and the space between the two is not normal empty space. It is an almost perfect vacuum, the emptiest space that exists in the universe. The density of matter in intergalactic space is approximately 1 atom per cubic meter. In some places, 1 atom per several cubic meters is a vacuum of a purity that we could never recreate in a laboratory. It would take 12.5 million years to reach Andromeda with starshot technology. Approximately 25 million years have passed since the first apes began to evolve in Africa until today. You would need half of that evolutionary time to make that journey. By the time you arrived, if anything arrived, humans would have evolved into something completely unrecognizable or would have become extinct long ago. But Andromeda is the exception. It is part of our local group, a collection of approximately 54 galaxies gravitationally bound to each other. The local group is approximately 10 million light-years in diameter. Within this group, there are perhaps half a dozen galaxies that we could theoretically target with spacecraft. The Triangulum Galaxy, 3 million light-years away. The Magellanic Clouds, dwarf satellite galaxies of the Milky Way, at 163,000 and 200,000 light-years, respectively. These are our cosmic neighbors, our immediate galactic family, and yet they are so incomprehensibly far away that reaching them would require technologies that push the limits of theoretical physics and time periods that exceed the history of our species. Beyond the local group, distances become truly cosmic in scale. The nearest galaxy cluster is the Virgo cluster, approximately 65 million light-years away. It contains approximately 100 galaxies. With starshot technology, it would take 325 million years to reach it. Dinosaurs ruled the Earth for approximately 165 million years. You would need almost twice that entire period to make that journey. And Virgo is our local supercluster. Beyond it are other superclusters, each containing tens of thousands of galaxies, separated by cosmic voids hundreds of millions of light-years across. The Coma supercluster is 330 million light-years away. The Great Attractor, a gravitational anomaly toward which our local group is moving at approximately 250 million light-years. Shapley, the most massive supercluster in our nearby universe, approximately 650 million light-years away. These places are so distant that the light we see from them left when dinosaurs still ruled the Earth, when the first mammals were mouse-sized creatures hiding in burrows. We are seeing the deep past of these places, and reaching them would require technologies and time periods that are simply incompatible with any meaningful concept of civilization or even biological species. And all of this is still within the nearby universe. The observable universe has a radius of approximately 46.5 billion light-years. That is due to the expansion of space. Light from objects now at that distance has taken 13.8 billion years to reach us, almost the entire age of the universe. But those objects have moved away due to expansion while their light was traveling. But remember the Hubble horizon we discussed earlier. Beyond approximately 4.6 billion light-years, galaxies are moving away faster than even light can travel to reach them. Approximately 94% of the galaxies in the observable universe are beyond that horizon. They are observable in the sense that we can see their ancient light, but they are unreachable in any practical sense. Astronomers use something called the cosmic distance ladder to measure these vast expanses. It's a hierarchy of methods, each calibrated against the previous one, each extending our reach a little further. Stellar parallax for nearby stars, Cepheid variables for nearby galaxies, Type Ia supernovae for cosmological distances. And each step on this ladder reveals that the universe is even vaster than the previous step suggested. There is something deeply humbling about mapping the universe accurately. It's not just that we are small, although we are. It's that we are trapped in a tiny region of an incomprehensibly vast cosmos, with no conceivable way to escape that region. It's like discovering that you live on a tiny island in an infinite ocean, except that this ocean is made of lethal vacuum and is actively expanding to ensure that you can never swim to another island. There are approximately 2 trillion galaxies in the observable universe. 2 trillion. Each containing hundreds of billions of stars, each star potentially with planets. The number of potential worlds is so vast that we literally cannot comprehend it. And of all those worlds, of all those possibilities, our species has meaningful access to exactly one Earth. With extreme effort and advanced technology, we might be able to colonize a few other bodies in our solar system. Mars, probably. Perhaps moons of Jupiter or Saturn. With a lot of luck and multiple technological leaps. Perhaps we could send generational ships to some nearby star systems, establishing small colonies that would probably die out or evolve into something non-human. And with technologies that border on the impossible, and resource commitments that exceed anything our civilization has ever done. Perhaps, just perhaps, we could send expeditions to other galaxies in the local group. Expeditions that would take millions of years, that would completely break communication with home, that would be essentially irrelevant to the civilization that launched them. This is the map of our prison. a pale blue dot suspended in a sunbeam, as Carl Sagan called it. Surrounded by a solar system that we could marginally explore, contained within a galaxy that we could theoretically navigate for millions of years, and that galaxy floating in a local group that marks the absolute limits of any conceivable expansion. Beyond those limits, the universe continues on scales that make our largest numbers seem trivial. But for us, for any biological civilization limited by the laws of physics, those expanses might as well be infinite. They are unreachable, not because we lack the technology, although we do, but because the fundamental laws of the universe guarantee that they will forever remain out of reach. And yet, despite all this despair, despite all these insurmountable barriers, humanity continues to dream of the stars, continues to imagine warp drives and wormholes and dimensional shortcuts that would allow us to circumvent these limitations. It continues to cling to the hope that science fiction will eventually become scientific reality. So let's examine those hopes one by one and see if any can survive an encounter with real physics. For decades, science fiction has sold us a vision of the future, where humanity escapes its planetary prison and expands into the cosmos. Star Trek showed us the warp drive. Star Wars gave us hyperspace. Battlestar Galactica introduced us to instant FTL jumps. Interstellar seduced us with traversable wormholes. These stories are beautiful, inspiring, full of hope, and all, absolutely all, depend on physics that is either completely impossible or so deeply improbable that we might as well call it magic. It's not the writer's fault. Their job is to tell exciting stories, not give physics lessons. But they have created generations of people who genuinely believe that intergalactic travel is just a matter of time and technological development, that we will eventually discover the trick, the loophole in the laws of the universe, that will allow us to circumvent the limitations. So let's examine the most popular solutions in science fiction, and let's see why each one falls apart when you confront it with real physics. Let's start with the most iconic, the Star Trek warp drive. The idea is elegant. Instead of moving the ship through space, you contract the space in front of you and expand the space behind you. You create a bubble of space-time that carries you along as you surf a wave of distorted space. Technically, you're not traveling faster than light through space, so you're not violating relativity. Space itself moves, and you go with it. This idea isn't completely made up. In 1994, physicist Miguel Alcubierre published a paper showing that Einstein's equations of general relativity technically allow for this geometry of space-time. The paper caused excitement because it seemed we finally had a mathematical solution for faster-than-light travel that didn't openly violate known laws. But the excitement was short-lived. When physicists examined the equations more closely, they discovered devastating problems. The first is energy. To create a warp bubble the size of a spacecraft, Alcubierre's equations require amounts of negative energy equivalent to the mass energy of the entire Jupiter. Negative energy. We're not talking about antimatter, which is normal matter with opposite charge. We're talking about energy with negative density, something that has negative pressure and repulsive gravity. Negative energy exists. Technically, there is a quantum phenomenon called the Casimir effect, which produces tiny amounts of something that behaves like negative energy. Two metal plates extremely close together in a vacuum experience an attractive force due to quantum fluctuations. But the amounts are ridiculously small, on the order of piconewtons, and no one has any idea how to amplify this to macroscopic amounts, let alone to the mass energy of Jupiter. But let's assume you can magically generate negative energy. The second problem is causality. Subsequent analyses of Alcubierre's metric show that you inevitably create closed time-like curves, loops in time that allow violations of causality. You could arrive at your destination before you left. You could be your own grandfather. The universe becomes filled with logical paradoxes that break the basic coherence of reality. Physicists generally believe that there is something called the chronological protection conjecture. The universe has built-in mechanisms that prevent violations of causality. The laws of physics conspire to make time machines and any technology that allows temporal paradoxes impossible. If that is true, and all the evidence suggests that it is, then warp drives are physically impossible. Not because they violate special relativity, but because they violate something even more fundamental, the causal structure of space-time. There is also a third practical problem. Even if you could create a warp bubble, you couldn't control it from the inside. The equations show that once you are inside the bubble, you are causally disconnected from the outside. You cannot send signals forward to direct the bubble. You can't accelerate or brake. You can't change direction. You'd be trapped in an uncontrollable bubble, gliding through space, with no way to stop or maneuver. Not exactly useful for navigation. Okay, so the warp drive is out. What about wormholes? The idea is that space-time can be bent in such a way that two distant regions are connected by a tunnel. You travel through the wormhole and instantly emerge in a distant location. It's like folding a sheet of paper and punching a hole through both layers simultaneously. Wormholes actually emerge from Einstein's general relativity. They are mathematically valid solutions, but there are several catastrophic problems that make them useless for travel. First, natural wormholes, if they exist, would be microscopic and ephemeral. They would form and collapse in fractions of a second on quantum scales. To create a wormhole that humans could travel through, you would need to stabilize it. And the only known way to stabilize a wormhole is to fill its throat with enormous amounts of exotic matter, specifically that negative energy we discussed earlier. Again, the amounts needed are astronomical, probably equivalent to the mass of multiple stars. Second, even if you could stabilize a wormhole, traveling through it would be lethal. The extreme curvature of space-time in the throat would create tidal forces that would stretch you out like spaghetti. You would need to make the wormhole so incredibly large that the tidal forces become tolerable, which requires even more exotic energy. Third, and perhaps most devastating, you can't just create a wormhole by connecting two arbitrary points in space. Wormholes connect regions of space-time that are already connected in some way in the structure of space. To create a wormhole between Earth and Andromeda, you would first need to physically drag one end of the wormhole to Andromeda by conventional methods, meaning that the first trip still takes millions of years. The wormhole is only useful for subsequent trips, and ultimately, like warp drives, traversable wormholes inevitably allow time travel and violations of causality. If you have a traversable wormhole, you can turn it into a time machine by moving one end at relativistic speeds, which probably means that the chronological protection conjecture makes them impossible. What about hyperspace or extra dimensions? The idea is that there are additional dimensions of space beyond the three we experience, and that by traveling through these extra dimensions, you could take shortcuts. It's like walking across the surface of a sphere versus drilling straight through the interior. Modern theoretical physics, specifically string theory, suggests that extra dimensions could exist. But there's a problem. These dimensions are compactified, rolled up on themselves at incredibly small scales, probably around the Planck length. 10 to the power of 35 Menner. That's about 1,000,000 trillion times smaller than a proton. These dimensions are so microscopic that only fundamental particles can see or interact with them. Macroscopic objects like you or a spaceship simply cannot fit into these dimensions. It would be like trying to squeeze a continent through the eye of a needle that is a billion trillion times smaller than an atom. This is not an engineering limitation. It is a fundamental geometric limitation. Some have speculated about extra dimensions large enough for macroscopic objects to access, but we have no evidence of such dimensions, and their existence would create observable effects on gravity that we do not see. Experimental tests have set increasingly strict limits on how large detectable extra dimensions could be, and those limits are now so small that they are useless for travel. Okay. What about tachyons? Hypothetical particles that travel faster than light. If they exist, perhaps you could use them for communication or superluminal propulsion. The problem with tachyons is that they are mathematically consistent only if they never interact with normal matter. The moment a tachyon interacts with something, it creates causality paradoxes. Tachyons could carry information into the past, allowing effects to precede their causes. Most physicists believe that tachyons simply do not exist, precisely because they would cause these violations of causality. Even if they did exist, they would not help you. You cannot accelerate normal matter beyond the speed of light to turn it into tachyons. There is an insurmountable barrier at the speed of light. Tachyons, if they exist, would have been born traveling faster than light and could never slow down below it. They are completely separate and inaccessible objects from our subluminal point of view. What about manipulating the quantum vacuum? Some speculative papers suggest that the quantum vacuum, far from being truly empty, is a sea of virtual particles constantly appearing and disappearing. Perhaps you could extract energy from the vacuum or manipulate it to create propulsion. The problem is that the quantum vacuum is in its lowest possible energy state. It's like trying to extract water from a lake that is already at its lowest possible point. There is no net energy you can extract. The Casimir effect we mentioned earlier does not create energy out of nothing. It simply redistributes the zero-point energy that already exists. And the amounts are so minuscule that they are completely useless for propulsion. Every proposed solution eventually hits the same wall. The fundamental laws of physics are not laws in the sense of regulations that could be changed. They are descriptions of how reality works at its most basic level. Violating them is not like breaking a rule. It's like trying to draw a triangle with 4 sides or create a married bachelor. It's a logical contradiction, not just a technical challenge. Science fiction lied to us not out of malice, but out of narrative necessity. Stories about people trapped forever in a single solar system are not as exciting as stories about galactic empires. But the consequence of generations of these stories is that millions of people genuinely believe that intergalactic travel is inevitable. Just a matter of time and progress. The truth is harder, but also more beautiful in its own way. The universe is not designed for our convenience. It was not created for us to explore freely. The very laws that allow atoms to exist, that allow chemistry to exist, that allow life to exist, are the laws that guarantee our galactic confinement. There is no loophole, no clever trick, no future technological solution. The doors are closed, not with locks we can pick, but with the fundamental mathematical laws of reality itself. And those laws do not change. They are not negotiable. They make no exceptions. So what are we left with? If intergalactic travel is impossible, if all the speculative technology of science fiction is fantasy, if we are truly doomed to remain in our galaxy forever, what is the meaning of it all? Is this revelation a cosmic tragedy? Or could it be, paradoxically, the best news our species could receive? We have traveled a dark path together. We have faced distances that defy comprehension, energies that exceed what is possible, communications that break down in cosmic silence, a universe that actively expands to distance us from our destinies. Relativistic limits that close all doors, biological bodies that collapse under the conditions of deep space, maps that reveal our cosmic insignificance, and technological dreams that crumble under the scrutiny of real physics. It is easy to see all this as a tragedy, as a life sentence handed down by an indifferent universe, as the end of the great human narrative of exploration and discovery. We went from believing we were the center of the cosmos to realizing that we are conscious prisoners on a cosmic island from which we can never escape. It's devastating, it's humiliating, it's definitive. But there is another way to look at this truth, a way that transforms despair into something unexpectedly beautiful. Because our galactic prison is not a small, claustrophobic cell. It is a realm so vast, so rich in possibilities, so full of unsolved mysteries, that we could literally explore it for millions of generations, without running out of wonders to discover. The Milky Way contains approximately 400 billion stars. 400 billion. Each one potentially with planets. Conservative estimates suggest that there are at least 100 billion planets in our galaxy, and we're not talking about dead rocks floating in a vacuum. Recent studies of exoplanets suggest that approximately 20% of Sun-like stars have planets in the habitable zone, regions where liquid water can exist. That means approximately 20 billion potentially habitable worlds in our galaxy alone. 20 billion opportunities to find life, to discover alien ecosystems, to perhaps find civilizations with which we could communicate within reasonable time frames. If only 1 in 1,000 of those habitable worlds developed complex life, we would be talking about 20 million living worlds. And if only 1 in 1,000 of those developed technological intelligence, there would still be 20,000 civilizations in our galaxy. We don't need to escape the Milky Way to find cosmic company. We need to look more carefully at our own neighborhood. And that neighborhood is incomprehensibly vast. Even traveling to the nearest star would take us decades with advanced technology. To fully explore just our local sector of the galaxy, say a radius of 1,000 light years, would require millions of missions over thousands of years. That's work for 1,000 civilizations over 1,000,000 years, and that assumes we're only interested in planets. But the Milky Way is full of other fascinating phenomena. Nebulae where stars are born, star-forming regions so vast that they contain enough material for millions of suns. Binary systems where stars orbit in complex gravitational dances. Neutron stars spinning hundreds of times per second, with magnetic fields so intense that they distort atoms themselves. Black holes with masses of millions or billions of suns, where the laws of physics break down. Neutron stars that spin hundreds of times per second, with magnetic fields so intense that they distort atoms themselves. Black holes with masses of millions or billions of suns, where the laws of physics behave in ways we are only beginning to understand. At the center of our galaxy reside as Sagittarius A star, a supermassive black hole with approximately 4 million times the mass of the Sun. It is a natural laboratory for studying extreme gravity, relativistic physics, and the limits of our theories. Reaching it with conventional spacecraft would take tens of thousands of years. But it is within our galaxy. It is accessible in principle. It is part of our home. And then there is the complete structure of the Milky Way. It is a barred spiral galaxy with arms extending from a dense central core. It contains regions of different ages, different metallicities, different evolutionary histories. Explore how star formation varies in different parts of the galaxy, how chemical compositions evolve, how dark matter is distributed, These are all mysteries that will require centuries of observation and exploration to solve. But perhaps the most powerful argument for accepting our galactic limits has nothing to do with what we might find out there, but with what we can be here. Human history so far has been a story of constant expansion from Africa to the world, from continents to oceans, from Earth to space. And every time we reach a new boundary, we cross it. But now we have reached a boundary that we cannot cross, and that forces us to do something we have never had to do before. Stop and think deeply about what kind of civilization we want to be within the boundaries we have. For centuries, we have operated under the assumption that there will always be more territory to explore, more resources to exploit, more frontiers to cross. This mindset has led us to destroy ecosystems, deplete resources, and operate as if infinite growth were possible. But the universe has just taught us a fundamental lesson. Infinite growth is not possible. There are absolute limits inscribed in the structure of reality. Accepting our galactic limits means accepting that we must learn to thrive within Mindenta, finite boundaries, that we must develop a sustainable civilization, not because it is morally superior, but because it is physically necessary. There is no planet B in another galaxy to which we can flee if we ruin this one. There is no escape from the consequences of our actions. This is liberating in a strange and paradoxical way. It eliminates the fantasy that we can simply move when things get tough. It forces us to commit fully to the space we have, to care for it, to build something sustainable and beautiful within our limits. And those limits are vast. I can never emphasize this enough. We are talking about a galaxy 100,000 light-years in diameter, 400 billion stars, 100 billion planets. Enough material resources to build structures the size of solar systems. Energy available from billions of stars. Enough space for trillions of human beings to live rich and meaningful lives. A civilization that could harness the resources of just 1% of the stars in the Milky Way would be a Type 2.5 civilization on the Kardashev scale, controlling energies equivalent to 1 billion suns. It could build Dyson spheres around stars, collecting every photon of energy they emit. It could build planet-sized space habitats, terraform worlds, create entirely new biospheres, and even engineer new life forms adapted to exotic environments. The challenges of building such a civilization would keep millions of generations busy. The problems of coordination between star systems separated by light years would require new forms of governance and social organization. The ethical challenges of interacting with alien life, if we find it, would require wisdom that we are only beginning to develop. And there is something profoundly beautiful about the idea that we are permanently isolated from other galaxies. It means that any intelligent life that arises in the Milky Way is our cosmic cousins. We share the same galactic island. We are bound by the common destiny of being trapped here together. We are not competitors for intergalactic resources, because no such accessible resources exist. We are potential collaborators in the project of understanding and inhabiting our shared galaxy. The impossibility of intergalactic travel also means that any intelligent life we encounter in the Milky Way evolved here independently of us. They are not invaders from other galaxies. They are products of the same cosmic evolutionary process that created us. That creates a basis for empathy and understanding that would be impossible with true aliens from other galaxies with completely disconnected histories. There is also a strange comfort in knowing that our limits are absolute. There is no pressure to achieve the unachievable. There is no guilt for not conquering the unconquerable. We can relax in the certainty that we have found the final limits, and within those limits, build something extraordinary. The Milky Way is not a prison. It is a perfect home designed by the laws of physics to be exactly the right size for a technological civilization. Large enough to contain infinite variety and mystery. Small enough for interstellar communication to be possible within human lifetimes. Isolated enough from other galaxies for us to develop our own unique identity without interference. And in approximately 4 billion years, Andromeda will collide with the Milky Way. The two galaxies will merge over billions of years in a chaotic gravitational dance, eventually forming a single giant elliptical galaxy that astronomers call a Milkomeda or Lactomeda. That merged galaxy will contain approximately 1 trillion stars, twice as many worlds to explore, twice as many mysteries to solve. By then, if we survive, if we thrive, if we learn to live within our limits in a sustainable way, we will be an ancient civilization beyond imagination. We will have had 4 billion years to expand across the Milky Way, to find and potentially collaborate with other intelligent life forms to build structures and societies that we cannot even imagine now. And when the galaxies collide, and keep in mind that the stars are so far apart that few direct collisions will occur, we will have a whole new merged galaxy to explore. New stellar neighborhoods formed by chaotic mixing, new regions of explosive star formation where gas clouds collide, new central black holes merging into an even more massive one. It's a whole new frontier that will open up automatically without violating the laws of physics. The revelation that we will never leave the Milky Way is not the end of human history. It is the beginning of a new, much deeper and more sustainable narrative. It is the transition from an adolescent species that believes it can conquer the infinite universe to a mature species that understands its limits and chooses to thrive within them. Limits are not prisons. When you accept them, they become definitions of home. The walls that confine us also protect us, define us, give us identity. We are and always will be children of the Milky Way, born of its stardust, evolved under its light, destined to explore its mysteries for as long as we exist as a species. This is our galaxy, our home, our destiny, and it is more than enough. It is perfect. It is all we will ever need. The stars we see in the night sky are not unattainable dreams of escape. They are our distant neighbors, waiting patiently for us to mature enough to visit them. The universe has taught us a lesson in cosmic humility. It has shown us our place, not at the center, not as conquerors of the infinite cosmos, but as conscious inhabitants of a galactic island. Exquisite, floating in a sea of emptiness that we will never cross, but that we also do not need to cross, because within this island there are enough wonders for 1,000,000 lifetimes, enough mysteries for 1,000,000,000 questions, enough space for every conceivable form of human and post-human life to flourish for eons. We will never leave the Milky Way, and that is not a tragedy. It is the most liberating truth our species could learn, because it means we can finally stop looking outwards with envy and start looking inwards with wonder. We can stop dreaming of the impossible and start building the extraordinary within the possible. Our galactic prison is paradoxically the greatest freedom we could ask for. And within its absolute limits, we will find not the end of our story, but its true beginning. If you've made it this far on this journey through the impossible barriers that confine us, if you've faced these devastating truths without looking away, then perhaps you're ready for the next step, to join those who look at the cosmos, not with fantasies of impossible conquest, but with deep appreciation for the extraordinary home we already have. Stay with us at Night Science, where we will continue to explore the limits of what is possible and find beauty in the truths that the universe reveals to us, however hard they may be. Yeah.